Hi all, welcome back to Ashkemi. So today we'll have the part 8 of the question paper discussion that we were so far discussing, and this video is exclusively for an analytical technique which is known as polarography, because only one question is included in this video, but it discusses all the aspects of polarography and will be useful for anyone who are unaware of this method. So for those who have not gone through the previous video, I've created a playlist in the channel, and moreover you can get the link through the iCard above. And without wasting much time, let's get started. So the question that we have to discuss in this video is question number 31 of the question paper, which is based on limiting current in polarography. Limiting current in polarography depends on residual current, diffusion current, kinetic current, all the above. So for answering this question, we need to have a discussion on polarography. So let's have a short discussion on that. Polarography is actually a method which is used for the analysis of electroreducible or oxidizable metal, ion or organic species. That is, suppose you want to analyze a solution containing a electroactive species. That is a species which can undergo either electroreduction or electrooxidation. So if you are having such a type of species and you have to find out the concentration of that species in the solution, you can make use of this method. Now, when you look at the instrumental setup for the same, you can see that the main components of a polarographic instrumental setup is that it consists of a couple of electrodes. That is, here you can see that there is dropping mercury electrode, and here you can see a counter electrode. Reference electrode is not always required. So when you look at the dropping mercury electrode, it is known as the polarizable electrode. Polarizable electrode, and it will be acting as the cathode. Whereas the counter electrode will be non-polarizable and it will be acting as anode. Okay, so these electrodes are very important in polarographic experiment. So suppose you have taken the solution of the electroactive species in a container, and to this you have dipped two electrodes, and this is the dropping mercury electrode which is acting as the cathode, and this is the platinum electrode which is acting as the anode. Now, suppose you are analyzing a solution containing cadmium 2 plus ion. Cadmium 2 plus ion is a electroreducible species because it can undergo reduction to cadmium atom by accepting two electrons. Okay, so you'll be taking this cadmium solution in the container which is having the two electrode, and you will be applying a voltage between the two electrodes. Then you can see that a current flows through the solution, or current flows across this electrode, and by measuring the amount of current you can determine the concentration of the electroactive species. Now when these electrodes are, when a potential is applied between this electrode, what is leading to the current flow? So that in order to understand that, consider that I have already mentioned that this container contains cadmium solution, cadmium 2 plus solution. So cadmium 2 plus solution contains lot of cadmium ion, and when you apply a potential, this cadmium ion starts moving towards the dropping mercury electrode, and at dropping mercury electrode it accepts two electrons and will get reduced to cadmium atom. So this is the reaction that is taking place at dropping mercury electrode. And when time elapses, there is you'll reach a certain point where concentration of the cadmium ion around the dropping mercury electrode will be low, and concentration of cadmium ion on the other part, that is on the side of the non-polarizable electrode, will be high. Okay, why this is happening? That is happening because in the region near this dropping mercury electrode, cadmium atom ion is getting reduced to cadmium atom. So here you can see only cadmium atom, not cadmium ion. But on the other part of the solution, there is more concentration of cadmium 2 plus, because this is a non-polarizable electrode that is not able to reduce this electroactive species. So this will lead to a what is known as a concentration gradient. That is, there is a concentration difference between both the sides of this electrode or the solution or the cell that we are talking about. Therefore, this lead to a concentration gradient, and this concentration gradient is responsible for the current flow. And when you determine the amount of current, that is always proportional to the concentration of the electroactive species that you can obtain from a graph, and we'll have a discussion on the graph in the next slide. So this is the summary of polarography, and we need to have some other constituents for this instrumental setup. So we'll have a discussion on that too. So in the last slide, we have seen that the movement of cadmium 2 plus ion towards the dropping mercury electrode for reduction to cadmium atom is responsible for the current flow. That is, when this happens, there is a concentration difference of cadmium 2 plus across the electrode, and that leads to current flow. Now, when you consider the mode of transport of the electroactive species, that is, for example, if you consider the cadmium 2 plus ion, that can actually take place through three different methods. That is either by convection, by electrostatic attraction, which is also referred to as the migration, and by diffusion. So these three are the methods by which the modes by which the electroactive species can transport or move towards dropping mercury electrode. But in polarography, we mainly focus on the diffusion method. That is, the current that we obtain is solely the diffusion current. That means we are eliminating the possibility for other current like convection or electrostatic attraction, and the method by which we eliminate these currents are very important because that can also be asked as a question regarding polarography. That is convection current. That is, we can prevent this convection current by mechanical stirring or by heating. That is, if you are stirring the solution throughout the analysis or by heating, it will increase the convection current. So, we can prevent this by we can avoid this convection current by preventing mechanical stirring or heating. That is, this can lead to convection current. So, in order to avoid that, or in order to completely rule out that possibility, we have to prevent or we have to avoid stirring, and we have to control the temperature, and this can be also done by using some gelatin to increase the viscosity. So when the viscosity of the medium increases, then that will not undergo stirring and all. So these are some method by which you can prevent convection current. Now coming to the migration current, and that is due to the electrostatic attraction between the positive species and the negative cathode, and this can be prevented or minimized by adding excess of inert electrolyte. That is, usually in polarography we'll make use of a supporting electrolyte. We'll be having a solution of the analyte as well as we'll be having a supporting electrolyte. The function of the supporting electrolyte is to prevent electrostatic attraction, and moreover, the concentration of the supporting electrolyte will be 50 to 100 times larger than the analyte concentration. That is a special condition that you have to apply for the supporting electrolyte. That is also a very important point regarding polarography, because that is also asked in many questions. So you have to note it down. Now coming to diffusion process, diffusion current is actually taking place, or it is formed when there is a concentration gradient of the ion. So when there is a concentration gradient, a current flow occurs, and that corresponds to diffusion current. And in order to concentrate polarography solely on this diffusion current, you have to prevent convection and electrostatic migration current by the method that we have already discussed. So diffusion current is mainly due to concentration gradient, and that is depicted in a figure like this. that is M plus ion. Suppose you are having a general representation for electroactive species M plus, that will move towards dropping mercury electrode and will be getting reduced. So when you consider the concentration of M plus ion, it is higher in this side and lower in this side. So that leads to a concentration gradient and that will lead to a current flow. Okay, so these are the modes of transport of electroactive species. So these are some of the extra points that you need to understand regarding polarography. Now coming to the graph that we obtain as a result of a polarographic experiment, that is known as the polarogram. So this is the graph that we obtain. It is a plot of current, in particular diffusion current. Diffusion current you have to determine from the graph. The y-axis is current and the x-axis is applied voltage. So when you carry out a polarographic experiment, you'll be getting a S-shaped curve. This curve is somewhat S-shaped. So here you can see different forms of current. Like here, this portion, that is the portion AB, that correspond to residual current. That is up to point AB that correspond to residual current. Residual current is nothing but it is a current which is present always when there is no applied voltage. Normally, diffusion current will be formed only when there is a concentration gradient, that is when you carry out the polarography. But even when you have not applied any voltage, you can actually find a current flow, and that current is known as the residual current. So till the point B, that is the decomposition potential of that electroactive species. Now when it comes to the point B, from there you can see that the diffusion current start arising, and there is a maximum point for this current. That is, even when you are from this point, you can understand that when you are going on increasing the potential, the current goes on increasing, but it will reach a limiting value where even if you further increase the potential, the current will not increase, and that corresponds to the limiting current. It arises essentially because the diffusion process have now attained a steady state. So when the diffusion process has attained a steady state, there is no further current flow. So these are some of the important points regarding the polarogram. Now what is diffusion current? From this graph, the diffusion current is actually the difference between the limiting current and residual current. Limiting current is a maximum possible current, and residual current is a current when there is no voltage applied. The difference between the two will correspond to diffusion current, and that diffusion current is actually proportional to the concentration of the electroactive species, and that is given by an equation known as the Ilkovic equation, which goes like this. ID, that is the diffusion current, is equal to 708 NCD raised to 1 by 2, M raised to 2 by 3, and T raised to 1 by 6. And here you can see the various values. That is N, it corresponds to the change in valency. For example, if you are considering the cadmium 2 plus ion, it corresponds to N correspond to 2. C is the concentration, D is the diffusion coefficient, M is the flow rate of mercury dropping. That is, you are having a dropping mercury electrode. So what rate the mercury is dropping. T is the lifetime of a mercury drop. How much time that a mercury drop persists, that is given by T. So substituting all the value, you can get the value of diffusion current, and the amount of diffusion current is actually proportional to, here you can see the concentration. So when you are by measuring the diffusion current, you can get an idea regarding the concentration of the electroactive species that is present in the solution. Now from the graph you can see another value known as the halfway potential. That is, you can actually see a curve BC, and the potential halfway of this BC, that is referred to as the halfway potential. The importance of halfway potential is that it actually gives the idea about what species is present. That is, halfway potential will be a constant for a given species. That is, if you are getting a value, say X, and if X correspond to a cadmium ion, then you can say that the solution contains cadmium ion. So this method is both qualitative as well as quantitative. You can determine what species is present and also what is the concentration of that species in the solution, right? So these are important points regarding the polarogram in a polarographic experiment. Now coming to the factors affecting limiting current. What factors affect this limiting current? There are 4 different factors. One is kinetic current, residual current, diffusion current, and migration current. So these three you have already gone through. And what is kinetic current? The kinetic current is actually the limited current which may be affected by the rate of non-electrode reaction called a non-electrode reaction, and that is known as kinetic current. So the current which correspond to non-electrode reaction, that is not happening due to the electrode process, that current is actually known as the kinetic current, and it is not represented in this polarogram, but you have to keep in mind that it is also a factor which is affecting the limiting current. So these are some of the factors affecting limiting current, and the present question that we are dealing with is actually related to this point. So we'll come to that later. So let's have a discussion on some other points regarding polarographic experiment. Another important point regarding polarographic experiment is that when you start this polarographic experiment, you'll remove oxygen from the solution. And what is the need of removing this oxygen from the solution before you start with the polarographic experiment? The reason for this is that oxygen is also a electroactive species. So in polarographic experiment, we are actually dealing with the determination of a electroactive species. But oxygen, it also happens to be an electroactive species. So instead of the analyte, oxygen, sometimes it can undergo electrooxidation or electroreduction, and that can affect the result of that polarographic experiment. So it's very important to remove oxygen from the solution before we start with the polarographic experiment. So what is that is the important point regarding this oxygen removal and how oxygen is removed. Oxygen is actually removed by bubbling nitrogen or hydrogen. That is, when you bubble nitrogen or hydrogen gas through the solution, that can remove oxygen. Now, if oxygen is present, I've already mentioned that it can interfere with the analysis. That is, it is also an electroactive species, so it can undergo electrooxidation or reduction. The reaction that corresponds to this reduction or oxidation is also important. You can just note it down, the equation. That is oxygen plus 2H plus 2 electron giving H2O2, and H2O2 plus 2H plus 2 electron giving 2H2O. So this is the reaction by which the oxygen gas undergo electrooxidation or electroreduction. So since this is happening, that can interfere with the analysis. Therefore, it is very important to remove oxygen. So that is done by bubbling nitrogen or hydrogen gas through the solution. Now, another important point regarding polarographic experiment is the appearance of something known as the polarographic maxima. That is, normally we accept an S-shaped curve for a polarogram, that is this black curve. But in some experiments, you can see that the graph will be like the red colored graph. That is, it will deviate from the S-shaped graph. And that is due to something which is known as the polarographic maxima. And the reason for polarographic maxima is that actually, the reason for polarographic maxima till now, it is not well known. The exact reason is not understood till now. And this can be eliminated. This can be eliminated by adding some agents, that is surface acting agent. And it is expected, I think it is expected as a result of some problem associated with the mercury drop. That is, when mercury drop falls on the solution, it leads to some kind of disturbances in the surface. That may be the reason for this polarographic maxima, and there is no clear idea about that, but it can be eliminated by making use of some surface acting agents. That is, surface acting agents. And the surface acting agents are like gelatin. You can note down these examples because they are really very important. Tritone. Triton is actually a Triton X100. It is a reagent that is used as surface acting agent. And agar is also sometimes used. And these are known as maxima suppressors. Maxima suppressors. That is the agent which helps in the suppressing of this maxima. That is, this curve can be suppressed to the S-shaped curve again by making use of these reagents like gelatin, Triton X100 and agar. And this is the important point regarding polarographic maxima, and this is also important because this is sometimes asked in many questions, so you can go through this one also. And the final point regarding the polarography experiment is that what are the factors which affect diffusion current? Factors affecting diffusion current. There are 4 factors. The first one is the concentration, that is given by Ilkovic equation. And the second one is temperature, and it is directly proportional to temperature. Third one is viscosity of the medium. And the fourth one is capillary characteristics of the medium. Okay, so these are the 4 different factors on which ID depend. So with that, we have come to the end of the discussion. Now we'll have the answer for the present question. So before looking at the answer for this question, we'll just have an important point regarding the dropping mercury electrode as well. What is the advantage of using dropping mercury electrode? That is, in polarography, most of the polarographic experiment, the polarizable electrode that we mainly make use of is dropping mercury electrode. And why you are using this particular electrode? And the major advantage of dropping mercury electrode, DME, is that each drop will have a smooth and uncontaminated surface free from any absorbed analyte or impurity. That is, when you are using a electrode, a solid electrode, the problem is that there can be a possibility of contamination because some materials or some thing can be adsorbed to the surface of this solid electrode. So this is not possible with a dropping mercury electrode, because at each time you are creating a new drop of mercury. Therefore, that is the main point regarding DME. It is free from all adsorbed analyte and impurity. The self-renewing electrode. So it is a kind of self-renewing electrode. It doesn't require processes like cleaning or polishing like the solid electrode. So normally when you have a solid electrode, you need to clean or polish after every analysis. So this is not required in the case of DME. And this advantage comes at the cost of working electrode with a constantly changing surface area. And moreover, the surface area also changes, that you can actually tune the surface area, and that is the importance of dropping mercury electrode. So this is also an important, these are some of the important point regarding dropping mercury electrode which you have to keep in your mind. Finally, coming to the question, that is, limiting current in polarography depends on, I think now you are in a position to answer this question. It actually depends on all these. That is, it depends on residual current, diffusion current, kinetic current, as well as migration current from the previous slide. So this is the answer. So the answer for this question is all the above. So that's all for this video, and with that I hope you might have got an idea regarding the analytical technique polarography. And if you have any doubt, you can just give a comment in the comment box, and I'll try to explain if possible. And I'll be coming soon with the next part of the video or next part of the question paper discussion. So till then, take care and bye-bye.